Good evening and thank you all for joining us today. My name is Rashmita and I'm the event planner for Microsoft Reactor Bengaluru, India. This session will run over the next 60 minutes, including Q&A. The session is being recorded and will be uploaded to our Reactor YouTube channel. I will share the link to our YouTube channel in the chat section soon. Before we begin, please take a moment to read our code of conduct. We are all here to learn together, so please be respectful of other people's views, understanding of differences, being kind and considerate in the way you engage. The chat will be open throughout, and we do encourage you all to participate. Also, please keep your mics muted during the session. I would now like to welcome Shivam, our speaker for today's session. Shivam is an author, cloud architect, speaker, and co-founder at TechScalable. He is passionate about technology and works on Azure, GCP, machine learning, and blockchain. He is also a Microsoft certified trainer. But for now, I will hand over to Shivam to begin the session. Over to you, Shivam.
Thank you, Rashmita. I will quickly share my screen. Okay, so good evening to everyone. Hopefully, all of you are doing well. You're at home and you're safe as well. So, basically, I will quickly walk you through the agenda for the day first. And we have a different type of session today. We generally work with uh, image data. We generally in machine learning sessions which we do, we usually work with the images as such, or we work with text as such. But this is today we are going to work with audio uh, over there. So we want to understand what are the various techniques when we have to process audio, and when we have to do any classification with that, then how does it work? So if I walk you through the agenda for the day, we basically will be taking care of the audio classification with PyTorch and Azure Machine Learning Service. Azure Machine Learning Service is the service where we do custom AI, where we design the custom AI solutions in Azure. The primary service is Azure ML Service. So we will be combining it with PyTorch to learn about the audio classifications. Okay, so now I'll walk you through the details over there, but this is the learn module link, which is there in the chat window. You can bookmark it, or you can also find this from the meetup page as well. If you open this link, it basically takes you to MS Learn over here, and where we have the introduction to audio classification with PyTorch. This is what we are covering in this session, uh, and we will be able to cover a subset of it because when you talk about audio classification, it goes pretty in depth. So this is where you will find the entire session in a very structured manner. You can go and read it, and you can perform the labs also over there. Now we basically, this module is having a couple of chapters or lessons or units over there. So if I click on the first one, I just want to show you something before I start. So for example, you don't even need Azure subscription to do these tutorials over here to learn the audio classification using PyTorch. You simply have to log in with any email ID over here, and then you can activate the sandbox. So sandbox is an environment where you can do this particular learn module, and you don't need Azure subscription to do it. They will provide it to us, right? Like that. So sometimes this is even better, right? Now, if I just go one unit back, and so let's get started with it, right? We'll understand the problem statement. We will understand a couple of we have a lot of concepts to understand today. A lot of words are there, a lot of terms are there. So I have these I looked up for various images on internet, and I have kept these images here. So I'll walk you through these images, and the ending will be very easy with convolutional neural network, like how it really works with CNN. But how do we reach that part when CNN is there? That journey takes time. So we'll understand a lot of things on the way. So before I do that, I just want to start from the learn module only. So you all of you must be having various type of voice assistant at your home, right? Cortana, Siri, Alexa, uh, all of these are there. So the or any other voice assistant which you use at home, right? Now these voice assistant, they basically use uh, three similar steps which we have in the screen right now. What they do, they first convert the speech to text over here. Once the speech has been converted to text, then it basically the text is then it runs through one NLP step now, which turns the word into numeric data. That word becomes the numeric data, and then it is converted. We covered that earlier, so we also actually did that in previous sessions. Now, finally, that classification of the utterance happens after that. Like whatever that word is, for example, you want to say switch on the switch on the light bulb, switch on the fan, turn off the light, turn off the something like that, right? Whatever. Now switch on the AC, like that. So that is basically your utterance getting classified in the intention. So as an intention over there, like the utterance is whatever we are speaking, or utterance is whatever you are typing also in chatbots normally. So the intention is like the intent of the customer or intent of the person who's speaking. Like what do they want to do? Like turn off the let's say start the music, play some particular song, uh, then which song, and so on and so forth, right? So then a classification step happens over there, and whatever your intention is, that thing will happen. Like you want to increase the volume, Alexa will increase the volume or decrease the volume, and so on and so forth. You already know all that, right? So these are the three steps which happen, like speech to text. Then the text is basically converted into numeric data, and then the classification of utterance into intention over there. So we will also do that now. So what we have with us is basically uh, I'll walk you through a couple of more terms before we can start. We have to understand a couple of things. Now I'll use this the learn module and the definitions which are there along with the diagram which I have. So basically the de facto way in which we the speech is captured is via microphones. So microphones, they basically are transducers as such. The transducer basically convert one form of energy into another. So today we have to go through a lot of this physics, right? Lot of different type of waveforms will come, a lot of terms will be there. So just hang in with me for next maybe 5 or 10 minutes. Then once we know all the terms, it will be easy for us to go through the module or go through the code over there. So what Microsoft phones are doing, they are converting one form of energy into another form of energy. So they convert the sound energy or sound waves into electrical energy as such. Now that electrical analog signal is it goes through one ADC device, analog to digital converter. What that does, it converts that analog signal to digital signal as such. This is where we have 010101. This is what computers understand. So now if I show you the same better colored diagram over here. I just took it from internet. I don't own these images, right? Whoever made them are the owners of them. So basically, this is the microphone, which when this is so this is the analog sound signal. This is analog electrical signal, and from here, this is the digital converter, which is converting that analog electrical signal into the digital signal over there, or digital output over there. This right side we are right now not concerned about. We are concerned about the what happens over here. Like we want to understand all the details about what is going on in this side over there. Now if I just walk you through a couple of more images which I have over here. So this is one, you see this analog signals are there. So this is how that analog signal may look like. It may not be so symmetrical. It will be a little wavy, but this is pretty symmetrical. So I got this from Wikipedia. So they have the most symmetrical image over there. Now you see these sample points over there. Now you must have heard one thing. When you purchase any audio device, any good speaker or any good microphone, though those microphones basically will have some sort of rating on it, like uh, 48 kilohertz, like that, or 16 kilohertz, like this, right? Some sort of rating will be there on top of it, like what is the sample rate. So this is basically what we call as a sample rate. So like how many samples are taken per second is the sample rate. Oh, sorry. Okay, so how many samples are taken per second is the sample rate. So what do you mean by sample, right? If I take you back to the signal over here, you see these samples which we are taking, the red lines which are there. This are samples we are taking. So 48,000 samples are taken in 1 second. So that is 48 kilohertz as such. Now, okay, now. So this is called a sample rate. Pretty important for us. Sample rate, one term. It will come many times. Okay, apart from this, so if we just read through this paragraph over here, we don't have much theory over here, but check this out. Higher the sample rate, higher the quality of the sound. However, after a certain point, the difference is not able to be detected by the human ears. Our human ears are able to understand till one point. Beyond that, they don't differentiate between the sample rate. Uh, Animals, they do it even beyond that. So your pets, if you have dogs at home, they listen to the sample rates, which are even beyond the frequencies are even beyond what we can listen to, right? Now, okay, so data which we are using is sampled at 16,000 samples are there per second. So we have 16 kilohertz over there. So 48,000 samples per second is 48 kilohertz over there. And you know what is sample? Sample is basically that. Like how much you see the red point, like sample value. You have taken some value. So how much that how many times that was taken in 1 second. Okay. Now if I take you back to the learn module over there, couple of more things over here. You see, the when the audio is sampled, it's sampling the frequency or the pitch of the sound and the amplitude of the sound. So when we sample, there are two things: pitch, which pitch or frequency, and amplitude. Amplitude is literally how loud the audio is. If you right, that's the meaning of it. So if I show that same thing, so I have the frequency or the pitch over here. This is how the high frequency versus low frequency uh, the waves will look like. This is high frequency. This is low frequency. It's like you can say the period is more between two of uh, the peaks or the between these points over there. Now, uh, the meaning of amplitude is over here, like how loud is the audio. So literally, like you can see in the screen. So the amplitude is also is also sampled or captured. I'll use the word captured during sampling, and the frequency as well. Now there is one more thing called as a waveform. You see this? That's one waveform over here. It's the graphical representation of that particular wave as such. Now, the signal can be represented as a wave, which is a signal representation over time in a graphical format, the one which I just showed you. The audio can be recorded over different channels. Channels like in stereo channels are there, left and right, two channels are there. And you may also have some devices. We all have devices which have more channels also, 5 channels or 7 channels and so on and so forth. Now, okay, so one more thing which we want to understand is that we split the audio files into frames. So if you have a very big audio file, then you want to segment it or you want to have small frames out of it. The sections of the audio can be classified individually to understand the intention of the customer or the person who's speaking into it. So if I show you that the frame will be looking something like this. So this is one picture where we have 50% overlapping frame. You see this? This frame is overlapping with that frame. That's third frame, fourth frame, and so on and so forth. It's not that you always take it 50%, but this is one image which I found. So, but we have in PyTorch, in Torch Audio, we will be having the capability uh, of specifying how much overlap do we want. And overlap will be able to preserve your context. Like when you are speaking something and you frame it out, then to preserve the context, you can say that you can have somewhat overlapping things over there. Now, so this is basically how frames will be can be visualized or looked at. Okay, if I take you back to the to the module over there. Okay, now the easy part starts over there. There are few more terms we have to go through. We'll go through them in some time. Now, basically, how do you do it? Like if I have to work with audio, basically the main service in Azure is called as Azure Machine Learning Service, which I have over here. So I went to my Azure portal and I deployed this machine learning service over here uh, as such. And sorry, and I have clicked on the Launch Studio after that. And once I have launched this studio, basically the next page opens over there, which is what I have here. This is called this is the interface of Azure Machine Learning Service. Now on the left hand side, we have many things over here. Notebooks. That's what we are using. AutoML is also there. Auto machine learning. And designer is the drag and drop functionality, which by which you can create your solutions. Dataset is dataset is what we are also using. Dataset basically will be of two types, tabular or file dataset. Now we are working with a lot of files. I'll show you my dataset as well. I have it open in my actually in my laptop right now. So what I have done, I have let me try to zoom in. Okay. Okay, so basically you see all these different folders, bird, right? So I'm not sure if you will be able to hear it or not, but if I play this, this is a bird, like someone is speaking bird over there. So like various different accents are there, uh, and we have that some same data set over there. Like everybody's speaking bird, one word only, and it's 1 second long. It is a toy data set, so it's one word and 1 second long. Now, so bird, cat, dog, eight, four, forward, happy, left, all the words are there. All the different audio files are there. And there are various, like three, then we have various audio files over here. Now, in PyTorch, multiple audio files are supported. You can work with, these are WAV formats. You can have other format of your audio files also, right? So, okay, now basically this is what the dataset is looking like that. Now the dataset is also pretty big in size, and dataset is also and I will also personally would not like to keep the dataset on-prem in my laptop. And while I was setting up the example, this demo, because here deep learning comes into picture, my laptop got stuck 3-4 times. So I avoided using my laptop, and obviously should have used the cloud in the first place. But now, so what we do, we generally uh, go back to Azure, and in Azure, we should be having one data lake with us like that. And inside this data lake is where we upload the data, either storage account or data lake. We are working with unstructured data. And if I zoom out, this is how it should look like over there, like this. So you see this? This is where we have the data right now. Now, this when you upload the data over here, for example, let's say I have this container called as data, where I have the data, where I upload the data. Now, this container will have all those different folders and those files over there. And there are hundreds and hundreds and hundreds of files, audio files inside each type of class which I have. Like bird is having hundreds of files over there. So what I do is basically so the logical or the most obvious way of doing that is making a data set. Data set will be we'll go for this data set and we will make the file data set over there. So this is a data store. Data store is representing the data lake. So get the data from the data lake. That's what we are thinking of. And file data set basically point to the path, and then you have to recursively read the files from there. So this is something which is useful for us. Experiments are experiments where all the logging happens. When you do any experiment, the logging happens over there. It gets logged over there. Pipelines are not relevant right now, but pipelines are pretty important for ML ops type of scenarios, right? This is not really ML ops pipeline. This is a machine learning pipeline, but this pipeline get encapsulated inside the ML ops pipeline. You can check out a few of my previous sessions on that. Environment is not really relevant right now, but we are using PyTorch environment. So you can upload, you can use the default environments, or you can make your own environments, and these environments will have all the dependencies over there. For example, if I show you the dependencies right now, these are the dependencies which I need, which I have configured in the requirement.txt here. So torch audio, torch info, and so on and so forth. So this is what that environment file will contain, which we need during the model training or deployment of the model later on. Okay, this is where the trained model is saved, and then rest of the things are there. So what I have done, I have clicked on compute. I have created this compute instance. This is my development environment in the cloud. This is my training environment in the cloud, like that. So now this is the one which I'm using right now. If I take you back to my notebooks, and I have these three notebooks over here, which I have taken from the Learn module only. Uh, and if I walk you through the first one, which we already know, where we all know all the terms over there. So if I walk you through the first one over here, you will notice that we are doing simple things first. We are creating the directory over there, and this is where we are using the data set. Now, Torch Audio is providing the data set as part of the framework or the library. If you want to use your own data set, you just put it in any folder and you refer to it. So I'm using this speech commands over here. And I'm using the torch audio.dataset. Now, torch basically support two things: dataset and data loader. Datasets are datasets. Data loader are the iterators which wrap the dataset, and then we can loop into the data and we can load it. Now, so 36 classes are there, the way I showed you earlier, right? Tree, 7, happy, cat, up, and so on and so forth. Okay, now if we convert the sound to the tensor, then how will it look like? So this is the representation of the waveform. So the waveform is represented in the tensor as a tensor right now. So this is what we have done. Now, if we plot that out, because this is not very visual, you cannot visually see it, right? How does it look like? So the plot is very straightforward to understand. This is how that waveform looks like over here. Now, uh, uh, like this. So this is yes, basically yes or no. So, okay, this is no. That's how no looks like. When you say no, this is the waveform of no. And it has been sort of undersampled, like sort of sampling has been done on top of it, meaning we have further reduced it. The audio was the data was pretty large. So I sort of had to take even a smaller sample of it. Uh, Over there. You can work with more of it. So this is basically how these various type of commands this is yes over here, and this is no over here. Like that's no. So like that. This is how they look like. And bird and all those will be looking something like that. You can change it, and you can when you do the learn module, you can change the folder to bird and you can print it out and have a look at it. Right? How does it look like? Okay. Now let's go to the other part of the. So this is how we are. So what we have done over here is we are just simply understood what are the various terms over there. However, we are not done with the terms. We will check out a couple of interesting terms now. I'll take you back to the learn module over here, and I will zoom out and I will go to the next unit over there. So you basically change from the top. You change it from here. You click on the other one. I ran the experiment in the sandbox. So I don't want the output to go away. So that's why I have opened all the different tabs, and I ran it in the ML in the AML service as well as a backup, like over there. Now, uh, this seems to be the same one. I'll go to the next one. Okay, so now check this out. So this is where we have various type of transformations and visualizations of the audio. One you already know, the waveform which I showed you. That's one visualization of the audio. But there are a couple of interesting things which we have to understand now. Uh, uh, okay, there are many things as such. If you open the transform list of torch audio, it will show you a very big list over there. And all that list will also have a lot of You have to understand a lot of physics also to be able to understand what it does. But we are sampling it down for today. It's an introduction to the audio classification. So we don't have to go to the entire thing over there, but we have to check out the more, you can say, the most interesting part of it. So we are going to understand what is spectrogram, and the spectro and MEL spectrogram, which is ML is like it's coming from an MFCC, which is another type of MEL transformation which we do on the MEL scale. Now, okay, apart from this, there are a couple of more terms over here. Resampling, spectrogram, we'll see, Griffin limb, deltas are there, and so on and so forth. You may have to invest some time into going through them, but we are not using all of these. We just want to use just a couple of things. So first of all, we load the data using the data loader. So that's over there. Okay, so if I take you to the main part over there, so this is my yes train yes train loader, but for yes, this is train loader for no. So you see this, like this is the data set which is there. Batch size 1, shuffle true, number of workers 0. Number of worker is like how many workers will be parallelly loading the data. So 0 for now. If you put 2, then 2 workers are loading the data into CPU when you run it. So over there, now if I just take you further over there, this is the vector representation of yes. We already have seen it. This is the vector representation of no. We can also understand that. Now waveform we understand. Signal is the graph, is the signal itself. Let me find the spectrogram over there. So okay, now check this out. So what spectrogram does, this is over here. This is how spectrograms will be looking like. That's another representation of the spectrogram over there. Now what it does, it basically is the representation of the frequency versus time. Sorry. So what it does is frequency versus time. What was frequency? Frequency is what I have here, high and low frequency. So if I represent that versus time, this is how it looks like. I'll try to zoom in. If the picture further just blurs up, you can also just look up for this on internet, right? It might be taken from Wikipedia only. So this is how it looks like in this manner. So if I zoom out, so we can go back to the main file over there, right? So this is how spectrograms will be looking like. Now, what are they? A spectrogram is basically maps the frequency of an audio file and allows us to visualize the audio data by frequency. So frequency versus time is spectrogram. Now this image is what we will use to, okay. Now see, the interesting part of the audio classification is that if you can convert things into images, you can use convolutional neural network. Convolutional neural networks are amazing when they work on image data as such. They are best for, we can say they are pretty solid for image data. If you don't want to use the VITs, the vision transformers, the convolutional neural networks are the standards as such. So that's what we are using in the introduction today. So we would like to convert the audios which we have, those frames which we have into these spectrograms over there. And then these spectrograms will become the input of the convolutional neural network. And that convolutional neural network will be doing the classification of that on the output classes, like bird, fan, yes, no, dog, and so on and so forth. I may have hypothetically added some extra classes. I don't think if music was there, but you are getting my point, right? So CNN will be doing the classification, feature extraction, and the classification from the input images. So that image is basically your speech or your audio speech converted into the spectrogram. Now here we are using this, but there is another very important thing which I want to cover right away. Which is called as a MEL spectrogram. So this is how the spectrogram looks like if you don't in grayscale. Now, there is one more thing called as MEL spectrogram. This is something which is interesting, and this is what we want to We can also use it. It's part of the learn module. In my example, I have not used it yet. It will take a little more time to train, and it's there in the same example. We'll definitely you can go through it. Now, what MEL spectrogram does? See, the couple of interesting things, right? I will show you one definition which I found from internet itself. Now, it's over here, like the bottom part. Very interesting thing. Now, see, the human ears. We just understood, right, that human ears they understand some frequencies. They are able to understand some particular frequencies, and some particular frequency they are unable to understand. Beyond one point, our ears doesn't make any difference. It doesn't. They don't find any difference. Now, so but there is another very important thing. Now, the our ears they basically perceive the sound different to how machines will perceive the sound. Like for machines, it will just be like some frequency, right? It will be like digital signal will be there, analog signal will be there. Computers will want that digital signal as such. Now, but humans they understand more. Like you understand what is melody, right? Like some voices are better, like have are more sweeter than others, and so on and so forth, whatever, right? Okay, now that's the melody is so that mel is referring to melody over there, but our ears our ear basically have higher resolution at lower frequency than at higher frequency, meaning so if we hear a sound at 200 hertz and 300 hertz, we can differentiate between them very easily. You can differentiate between the low frequency sounds if you hear two different sounds. But the difference, but if we try to find the uh, you can say, but it is difficult, or you need your ears needs to be more trained. This is where you need to have the music training and so on and so forth, right? Or maybe you're blessed with the music training itself, so your ears are more sensitive, or you understand it, like you perceive it better than what I will do, right? So these sounds, so versus when we compare the sounds at 1500 hertz and 1600 hertz, but technically the difference is only of 100 hertz. Like 200 hertz and 300 hertz is having a difference of 100, and similarly, the high frequency is also having the same difference. So from machine's point of view, it's just 100 hertz difference. But from human's point of view, you will not even differentiate. You will find it difficult, or at higher frequency, you cannot differentiate between the two sounds over there. You will not be able to understand the pitch of the sound, or the what you understand as the melody as such, in a sense. Now, whereas for the machine, the resolution is still the same. So it is noticed that the model. So okay, now why are we doing it here? It is noticed that the modeling. It is noticed that modeling the human hearing property at the feature extraction stage will improve the performance of the model. So this is very important for when we have to make them for humans. That's where it comes into picture. Now, so this is basically called as MEL scale, right? And this MEL scale is something which is mathematically has been, there is a formula which needs to be applied, uh, right? And there are more transformations on top of it after that. So, but I hope you understand the significance, or the layman meaning of it. Mathematical formula is something which definitely we can also uh, understand over there. Now, what I have done is basically after that, I want to take you to the next part. Okay, so we have the spectrograms or the MEL spectrograms. Both we can work with both of them. The normal spectrograms or the MEL spectrogram, which are made where we have the MEL scale versus the frequency, the time as such. So now whatever you have, these images are the inputs of your convolutional neural network. And convolutional neural network will be doing the classification on top of it. So I'll use one of the slides I generally use when CNN comes. So I'll walk you through a couple of slides over here. And this is the wrong end of the slide. So I'll just switch the slide. Okay, now check this out. What happens in CNN is CNNs, they work like this. We input various images and they extract the features, and the classification happens on top of it. So convolutional neural networks will be looking something like that, right? This is like little more in-depth view of convolutional neural networks. Now, one of the very famous convolutional neural network is this one called as VGT16. We are not making this today, but this is one of the pure convolutional neural network, or one of the one which is not having any other mechanisms like residual network and all that. This doesn't have it. The normal pure CNN. Now, we are making a subset of that, not this one as such. So just want to show you a couple of things, but we can go through this to understand CNN. There are various type of input images are there, different type of layers are there, pooling layer, convolutional layers, and so on and so forth. We stack them, and then the finally the features are extracted, and then we have the classification in the end of it. Now, uh, if I just take you through this slide again, three channels are there. RGB feature maps are here. Feature maps are simply the extracted the output feature maps, and the finally in VGG16, 4093 images are getting 4093 features are getting extracted of every image, and based on that the classification happens into 1000 classes. Okay, now convolutional neural networks, they have these typical layers are there. Convolution, pooling, and feature maps are there. When we work with binary image, that's how binary image look like. RGB will be looking like this. This is what I have in my example right now. Uh, and then and the images or this RGB plane looks like that, and we have RGB and plane, and the magnitudes are there to represent these colors. Now grayscale looks like this, and if I take you through the convolution layers over there, this is the meaning of how what convolution means. Like you have the convolution filter, and it is convolving over on top of the input image, or in middle of the architecture, then on top of the input feature map. Now the and this filter is convolving on top of it, and metric multiplication happens, and you see the output feature map here. We are getting the outputs over there. So this operation which is happening is called as convolutions, or this is one convolution which is happening over there. Now with convolutions, we are able to, with different type of filters, we are able to find the edges during convolution. So we can find the vertical edges, we can find the horizontal edges during convolutions. We have filters which can find many other different type of images, different type of edges. And if we can train the filter during the training process on our data set, it can find yes versus no, bird versus cat differentiation it can do on the input spectrogram images over there. Now, uh, this is stride. We are also using one stride. Stride is like when the filter moves on the feature map, like how many units does it move. Now padding is this. If your if the CNN architecture shrinks very fast, you do padding over there to be able to have more uh, layers in place. And if you don't do padding, it will shrink fast, right? Now, so I have this zero padding done on all four sides to be able to so the filter doesn't spill over, or it doesn't shrink. The entire thing doesn't shrink very fast. This is how when you have RGB plane, that's how the convolutions will be looking like. The filter is also having three channels over there, and then it is simply moving on top of the uh, input image, and then we are getting the output over there. Now, so in convolutional network, we learned the filter weights over there. Couple of things which we are also using will be ReLU. It's an activation function, which basically will convert all these negative values into zero over there. So it's a type of diminishing. It will diminish the features which are not really important, or you can say which are not really dominating. That's a better word, like not dominating in that part of the image. So max pooling is this, where we sort of take the highest pixel value or highest value as such in the output layer. So apart from max pooling, average pooling is also there, which basically takes the average of the values over there. So 2, 4, 5, 6 average is over there. So if we put everything together, this is how convolutional neural networks will look like. Now we are creating one convolutional neural network, but the purpose of our convolutional neural network is to classify the input audio spectrogram images into the output classes over there. So we will also do it. Now I'll take you back to the uh, to Azure, and this is the one where I'm creating it. So couple of normal things are going on here, and So basically, let me 20% data set. Train and test loaders are getting designed here. So if I can show this to you, batch size is 15. So 15 images will be in the batch size over there, and number of worker will be 2. So 2 workers will be parallelly loading the data, right? Like that. Now, the main thing is going, and if you have GPU, use GPU. I don't have it in this machine right now, so it's using CPU only. Now this is how we define the in PyTorch. This is how we define the neural networks over there, or the deep neural networks. We define them use in the you can say in this class over there, the neural network class over here, which is inheriting, or which is using the nn dot module of PyTorch. This is where all the layers are defined, right? If you look up for PyTorch nn dot module, you will find a list of the different layers which are possible. So we have these, we have this convolution layer 1, 2. We are doing some sort of, we are doing a dropout over here. It will do, it will try to, you can say, will not overtrain, or it will, you can say, overfit the network over there. One flatten layer is there, which will flatten out the output, and then linear layers are on top of it, and then finally, okay, so we have this, we define the layers, and how the, in the forward function we define how the data will be passed through these layers. So this is where we have the ReLU, the one which I was just showing it to you, uh, and maybe okay, I don't think if I have done any other thing here. Okay, so now this is how it looks like. Like, what is the kernel size? 5 cross 5. Stride is 1. How many channels are there? How many kernels are there? Then what will happen in the output? What the dropout will half it up. Like, it will, like one half of it will be left out as such. So over there. Now flatten will also flatten that, and then so on and so forth. So finally we use that, and we train the neural network over here. Now, we are just training it. We are just trying it out. So we have just randomly given 15 epochs over there, and the data set is slightly bigger in size. It will take some time for you to train it. So use the cloud, or use the uh, run this from the learn module in the sandbox. That will be suitable. And it basically will, so those epochs are going on here, and this is how the classification is looking like right now. So that what is the input and what is the output. So right now this is done only on two classes, yes and no. Like how you say no and how you say yes. You can totally use the entire data set. It will, like, which is having all the different classes, bird and dog and all of those. uh, so use that, train it on top of it, and all the uh, 30, 38 or 36 output classes, you use all the data, right? So this, so if I take you back to the learn module over there, and let's have a look at that. So this is what we have in the fourth unit, and this is what I also have shown you there. And then there is just a summary of it. So this is what I had for the session, and this is where we have. So we were able to understand the basics of the audio classification and how practically it works. So how various things what are the various terms over there? What is the meaning of sample, the sample rate? What is analog? What is this digital frequency, amplitude, waveform, and the frames, and how that waveform can be represented into the the spectrogram as such, and how CNN can take this as an input and throw the and divide your utterance into intention. So, and then from that point onwards, the smart IoT device which you have, or the smart voice assistant, then further can do that, like turn on the light bulb, increase the volume. If it classifies that volume increase, then increase the volume, and then like how much, maybe 30%, 20%, 40. So increase till that level. So this is how the audio classification with PyTorch looks and feels like. So if you have questions, please feel free to ask your questions, and also bookmark the learn modules so you can perform them. You don't even need the Azure subscription. A sandbox will be available for us to use over there. Now, there is one question in the chat: will CNN be relevant for audio input, or will RN be more relevant for audio input? It looks similar to NLP. Now, CNN is very relevant for the vision task. Now, these spectrograms over here are vision. It's basically these are images as such. So CNN is you can say behaving well, but uh, we have transformers today. There is another thing called as transformers. Transformers are based on RNN architecture. So transformers are also suitable for this, and transformers will also uh, may outperform the other you can say the convolutional neural networks. But the for transformers, you may need more technical expertise, and you will need lots and lots of more data to be able to do it better. So not many companies will be able to do that. So yeah, transformers which are RNN based are also suitable. Try that out. We did one session on transformers maybe a few weeks back.
So by PyTorch, can we identify the bird species by using the audio-based data
Yeah,
sets?
yeah. We
Okay.
literally have. I'm not sure if you able to hear when I click on it, or
No,
does it?
no, no,
No.
nobody.
Okay.
Okay.
So
Yeah,
right.
we
So
can.
if you
Yeah, go ahead.
when you will download this, you will also get the same data set, and this is literally the bird. The bird sounds are there, but right now the human being is speaking the bird. Like it's the word bird is being spoken by one lady right now in that file. So if you want to differentiate between various bird sounds, like
Yeah,
different type of,
species. I want to identify the species of a
yeah,
birds like crow.
pigeon versus,
Okay.
pigeon
Versus
versus parrot versus this, yeah, totally possible. You need to get the data set for that. Totally possible.
okay, okay. And also some bigger companies are using heartbeat sounds to identify if the patient is suffering from any diseases, right? Audio-based patients' heartbeat sounds.
I know a lot of like these convolutional neural networks or the vision based machine learning algorithms are dominating. I may not have much understanding of that heartbeat based like differentiation of whether your heartbeat is right now uniform or not. If it is not
Correct.
uniform, it's like
Yeah,
ECG, like audio ECG for your based on audio, I think.
correct.
Right? Okay. So okay, then definitely please do follow us on Reactor's meetup page and on LinkedIn as well. You can find me for your follow-up questions and join us. We have more sessions next week. The next session I think is just next week itself, and we will be back with with another interesting topic. So please do join and have a nice day as well.
Thank you, Shivam, for the session, and thank you all for joining us today. Please do share your feedback about today's session. Thank you once again, and happy weekend.